In this section, we're going to see how, given any periodic function, we can figure out what are the coefficients in its sine-cosine representation. Recall from the previous section that one of the forms of the Fourier series that we gave had a DC term, then it had this infinite sum that goes from frequency numbers 1 up through infinity, and this n here is going to be a multiple of the fundamental frequency. So recall that we're getting the lowest frequency and then all integer multiples of that. And when we add sines and cosines together at these frequencies, we don't change the fundamental period because each of these higher frequencies has a period that fits in an even multiple into the lowest frequency. So we have a sine and a cosine term. We start with the cosine term, which is a of n cosine, and then we have a frequency and a time variable here. The frequency is n times the fundamental frequency, and time, no phase shift. When we use this form, the phase information is taken care of by the relative weighting of the sine and the cosine, the odd and the even parts. And here's the sine part. Same frequency, n times the fundamental, and time. So the a and the b coefficients determine what the magnitudes of each of those are. Now, down below here, you can see equations 5.28. This gives the result that we're going to be deriving throughout this section. We see the DC term A0 is handled a little bit differently. In all cases, we do an integral over one period, and I will note here that instead of writing integral from 0 to t0, this will work for any period. So you could have any value t, and if you do a period that is t0 wide, you will get the same result. Now, we often symbolize this by having the integral symbol and just putting a t0 below. That is a symbol that's commonly used to say that you can integrate over any length of time that is t0 long, and you'll get the same result. So you should choose, when you evaluate this, what is the most convenient. It might be 0 to t0, or it might be minus t0 halves to t0 halves. They'll all give the same results. So we have the DC term A0, and we can see we're adding up all the area in x over one period, and then we are dividing by the duration of that period. So we'll get the DC average of the signal. That's A0. It's a special case that doesn't quite match the other ones. Then for n is 1 or more, the a and the b are found very similarly. The a, which is the coefficient of the cosine, is found by taking that same building block function or basis function, cosine n omega t, n omega not t, and multiplying it point by point by the function x, integrating over one period, dividing by the period, similar to how we had to do to the DC to get an average, and then multiplying by 2. And we're going to prove why this works. There's a few different ways that we can prove why the value 2 needs to be here. It'll get clearer also later in this chapter when we compare this with another form of the Fourier series called the exponential Fourier series. Once we prove how to calculate an or bn, the other follows very directly. We can see the cosine of a goes with the cosine here, the sine of b goes with the sine here, and the proofs are almost identical. One interesting thing I want to show you is if we look at the equation for a of n, and we try substituting in n equals 0. Now, we're not officially allowed to do that because these formulas here are for n is greater than or equal to 1. But what if we try that formula So we do the AN formula if n is 0. What if we try to get the DC term out of there? Well, let's see what we get. We get 2 over t0, integrate over a t0 interval, x of t times cosine of n omega naught is our frequency, but n is 0 here. So we'd have cosine of 0 dt, and that's just 1. So you end up with 2 times 1 over t0, the integral x of t dt. So we end up getting twice the actual a0. So that's why we can't just say use this formula for a0. We need a slightly different formula, but it almost works. The only difference is a factor of 2. What happens if we say n equals 0 in the EFN formula? Let's just develop a little intuition for what's happening here. So if I try that, so what's going to happen? I'm going to get b of 0 equals 2 over t0, integral over anything that's t0y, x of t times the sine of n omega naught t, sine 0 because n is 0, dt. This is times 0 here. So no matter what the function x is, I get 0. So we can, if we want to be very formal, we can say that if there is a b0 term, we can treat it as 0. But what this is saying is there is no DC component, that's 0, that is odd. There's no if it's an odd function, it cannot give me a DC value because it would have to change, assuming it's not equal to 0 on the left and right hand side of t equals 0. So that's kind of an interesting reduction, but there is no b0 term, or in some cases we like to think of it as equal to 0. Now, as we get ready to prove that these formulas work, we need some identities. And first slide, what we have is now these three formulas. So now that we have these three formulas, what we're going to do in the next section is we are going to, for some periodic function x of t that is not obviously made of sines and cosines, we're going to show how to find these coefficients. Your book has some integral of trig function identities that we're going to be using. So let's take a look at these. Property number 1 says if you take a sine wave and it has frequency omega naught, which corresponds to the period t omega naught, and if you have any multiple of that frequency, so 1 or 2 or 3 times it, you are going to get a complete you're going to get n complete cycles of the sine wave. So if n equals 3, I'm going 3 times the fundamental frequency, and I go over 1 fundamental period, so I will complete 3 cycles of the sine wave. So if I go from 0 to t0 here, it would look like that. So when I integrate a complete number of cycles of a sine wave, I get 0 as the area result. Doesn't matter what the phase shift is, because if I do a phase shift, whatever I lose off the left will come into the right on this fundamental period. Same thing works for a cosine. In property 2, if I integrate a cosine over an integer number of full periods, I will get area is equal to 0. Property number 3, we are not going to formally prove, but let's talk about some intuition of why this is true. Notice that property 3 applies when n and m are different numbers. So we are using different multiples of the fundamental frequency here. We have 2 sine waves being multiplied together, and they are at different multiples of the fundamental frequency. What's going to happen when we do this is that we are going to get positive and negative areas perfectly canceling out, and this will always happen when the frequencies are different. You could use a trig identity for sine times sine to simplify this, or you could use other approaches to prove that that area is going to be 0. But what's happening here is the positive and the negative areas still completely cancel out, and that happens regardless of the phase shifts. So that's an identity that we're going to need as well. Same thing happens for cosines. Cosines are just 90-degree shifts of sines, as you know, so the same thing will happen there. Unfortunately, in property 5, your book has an error. Now, the good news is if we make a slight correction to this formula from the book, we will get a correct identity, and it's the one that we need. So this statement number 5 from the book here is actually false. In order to make it true, we have to not have these phase shifts. It'll also work if the phase shifts are equal, but we don't need that in order to prove what we're trying to prove. So let's just set both of the phase shifts equal to 0. In that case, we have n and we have m here. Now above, we had cosine and cosine in identity 4 with different frequencies and arbitrary phase shift. So if I let these phi1 and phi2 here be 90 degrees apart in the correct way, I could get one of these cosines to become a sine. So when n and m are not equal, there's nothing interesting that property 5 is adding. So let's make this restriction in order to focus on what we really need and what the book really intended with property 5. For property 5, we are intending that this n and the m are equal. So let's just call this n here. So we have a sine and a cosine at the same frequency, which is a multiple of the fundamental. And if you go through a sine cosine formula and do a double angle simplification, you will show that it is indeed equal to 0 when I integrate over the full fundamental period. Another way of saying this is the sine and the cosine, we call them orthogonal functions because this being 90 degrees out of phase, the positive and the negative areas of their product do cancel out. So this simplified version is all that we need in order to prove the Fourier series coefficient formulas that we gave on the previous page are correct. Next formula says if I have a sine wave that is at a multiple of the fundamental frequency and I square that sine wave, I'm going to get this area. So what's happening here is I have a fundamental period. I have a sine wave that is at some multiple of it. So here I'm showing it as if n equals 3. And then if I square that, we are going to get this value right here. We have a double angle result. So the frequency doubles. And I have a amplitude here that goes up to 1. So now when we integrate that green curve over the entire period, we can see the area under it is half of the rectangle that contains it. And now I'm showing it here graphically, but this also, you can take the double angle formula through the integral and prove this. So the area of that orange rectangle is going to be T0 times 1, the width times the height. So the green curve carves out exactly half of the area because of the symmetry of the sinusoid function, and I am left with the area T0 over 2 as we have for property 6. And the same thing will happen for a cosine, that's property 7. So these trig identities are going to be trig integral identities are going to be what we need in order to prove that the formulas given on the previous slide, the formulas 5.28, give the correct Fourier series coefficient to describe any periodic function. So now we are going to prove that the definition that we gave for A0 is correct. First of all, remember that we are trying to represent the periodic function x of t in this form. So we have a cosine component at each multiple of the fundamental frequency, and we have a odd function or sine component at each multiple of the fundamental frequency. So the periodic function, that function for any coefficients a of n, b of n, and a of 0 is going to be periodic, and it can represent, with enough of these terms, any function. Now, given that the periodic function has that form, if I have it in some other expressions, such as unit steps or numeric values, how can I actually calculate what the A0 term is? Well, what we're going to do, since A0 is, we can see a DC offset here, in order to get that from x of t, what we're going to do in order to get A0 is we are going to take the function and integrate it from 0 to t0. We're going to take x of t and do that. And then we'll divide by the width of the integral. So that's going to be the DC average. And then we substitute in the definition for x of t with all its terms. And we see that we're going to have 1 over t0 times, okay, first term in x of t is a0. So all of these integrals are going from 0 to t0, so I'm not going to keep writing that. So I have that integral. And then I have the n equals 1 integrals. So I would have a1 cosine 1 omega naught t dt plus the integral of the next term. So integral of b1 sine n equals 1, so omega naught t dt, and we keep going. So we have integral of a2 cosine. Now we have the frequency n omega naught. And for b2, we have the frequency 2 omega naught again, because n is 2 here. And this series will go on infinitely long as the a and the b's are not 0. Now, what we do to simplify this is we see that the a1 coefficient is not varying with time, so we can pull it out of that integral there. And we do that with all the b's and all the a's except a0. Well, we can do it with a0 also, but we would just have times 1 in the a0 integral. Now, the integral of cosine that has the fundamental frequency over one period is going to have area 0. So we have this going to area 0 times a1. So there is the coefficient of a1 is 0 because multiplied by this DC value, we just get a multiple in amplitude of the cosine, and it's still going to have 0 area. Positive and negative areas will cancel out. That'll happen for one cycle of a sine wave as well. For 2 cycles of a cosine, the area there is 0, and the area for 2 complete cycles of a sine wave is also 0. So all these terms go to 0, and all that is left is right there. And if I simplify that, I have a0 times 1 over t0, the integral of 1 dt. And remember, this is an integral over a period t0. So this value here is just t0, so that cancels out. and I have left A0. Now, it maybe seems a little circular, but what we have here is a clever construction that's very powerful of x of t. X of t was represented in this form here with the sines, the cosine, and the dc term, so that when we wanted to extract the dc term, we would get just the dc component in A0 using this integral. We're now going to, on the next slide, going to show what happens for A1 when we are not at a dc term, but we're at a cosine. But the pattern is going to follow. When we try to extract A1 using the formula that we gave on the previous page, or on the first slide, we're going to see that the A0 part of the signal x disappears. It does not match up with the cosine that goes with A1. All the sine parts will disappear using the integral trig identities we had on the second slide. And then all the other cosines except the one where n is 1 will disappear. So that is the pattern in proving that the Fourier series formulas work. What we have here, for those of you who have had the linear algebra class, ME3032, we would say that each of these functions is orthogonal. So and since they are orthogonal, we can treat them separately, and they don't have interactions as far as contributing to power and so on when we do linear transformations of the signal. So the DC value, the cosine and sine at multiples of the fundamental frequency are all have integrals of 0 when you mix and match them. And that property is called orthogonality when you do the integral over one fundamental period. And because of that, we're going to get all these cancellations, and we're going to see that we can extract all the A and the B coefficients in calculus. We're going to show it for one example. We're going to show it for A1 on the next slide. The other proofs are similar. And then in the next video, we're actually going to do a concrete example and apply these formulas to an actual periodic function. So here we are starting out with the formula for the sine cosine form of the Fourier series, and we want to find the an and the bn coefficients when n is greater than or equal to 1. So let's find the an coefficients. So in order to do that, let's do the following. Let's multiply both sides of this equation by this term. So we have x of t. We're going to multiply it by cosine of m. So m is an integer, a different integer perhaps than n, definitely a different integer than m, omega naught t. So we multiply both sides. So the right side I get A0 cosine, and then I have this summation, and each term inside here is going to get multiplied by that cosine with frequency m omega naught. So I have an cosine m omega naught t cosine n omega naught t plus bn cosine m omega naught t sine n omega naught t. So that's what we get when we multiply everything through by that cosine. Now what we're going to do is we are going to integrate both sides of this equation over one fundamental period. You can think of it as being from 0 to t0, but it could be any fundamental period, and we will get the same result. And I'll integrate also what is on the right side here. Now, what's going to happen in this equation is a whole lot of these terms on the right-hand side, when they are integrated over one period, are going to vanish to zero, and we're going to be left over with just one term. So let's see what happens. Let's see what we can eliminate here. First, if we look at this first term and we just do the integral of this part over the period, what we're going to have is we have a cosine that goes through m complete cycles, and it's being scaled up by a DC constant A0. So we can take that constant A0 out of the expression, and we are just integrating cosine over m complete cycles. Well, all the areas are going to cancel out, so this first term does not contribute any value to the integral, because we made a careful choice of integrating it over an integer multiple number of full periods. That is the trick that allows us to completely eliminate this term. Next, we're going to take a look at the mixed cosine sine, where we have the frequency m omega naught on the cosine and the frequency n omega naught on the sine. First of all, let's consider what happens when m is not equal to n. In that case, we can use the integral identity number 3 or number 4, which says if I have sinusoids at different frequencies, and I multiply them together with any phase shift, the integral vanishes. Now, they're written in terms, identities 3 and 4, as sine times sine or cosine times cosine, but they work for any phase shift. So it doesn't really matter if it's a sine or a cosine if the area is proven to cancel out for any phase shift. So this term with the b of n is going to cancel out definitely when m and n are not equal. Now, if m and n are equal, so this is property 3 and 4. If m and n are equal to each other, then what we have is we have to go to property number 5 as we modified it. And on property number 5, we said if we have a sine and a cosine with no phase shift at the same frequency, their area is also 0. So when m and n are equal and when they're not equal, this term, the b, which is associated with the sine, vanishes to 0, having multiplied it by the cosine. So that term goes away no matter what m is, whether it's equal to n or not equal to n. So finally, what we have left is just the cosine term. And let me rewrite it here a little differently so we can get a closer look at what's going on. We have two cases. We have the case for all the n's that are not equal to m. So we have n equals 1 to infinity, where n is not equal to m, and we're holding one out of this sum, and we're going to come back and handle that one separately in a minute. So in these cases, what we have is we have a of n cosine m omega naught t cosine n omega naught t, and we do the integral for each of these functions over t0. The order of integrating and summing can be exchanged, so we can do each of these integrals and look at them separately, which we already talked about doing above for the b of n terms. So we have that term, and we have one left over, which I will write here explicitly. We have n and m are equal. So when n and m are equal, we have a of n cosine. Now the m is equal to n in this case, so I write n omega naught t. And that is actually equal to the second term when n and m are equal. So here we get a cosine squared. And that is also being integrated over a period t0. So now if we look at this first term, we have cosines at two different frequencies integrated over a fundamental period. So we have an integer number of m full cycles, an integer number of n full cycles, and property number 4 tells us that all of these cases where n is not equal to m, this goes to 0 by property 4. So all that is left is the term on the right with the cosine squared being integrated over one fundamental period. And if we look at property 7 tells us what to do with that. Property 7 tells us that this integral right here is going to have area t0 over 2. So now we put that all together. We have simplified this down and we have gotten a of n t0 over 2 is equal to what we started with. And what we started with was an integral over one complete period of the periodic function x of t times cosine of m omega naught t. And then we showed that this is the term that we have when m is equal to n. So in this equation, the m and the n are equal with what we have left, because that was the only one that didn't disappear up here. So now if I solve this, I can say a of n equals, and I multiply by 2 over t naught, t0, and then I have this integral right here. But m is equal to n. That is that was the surviving term a couple lines above, so this is n. There we go. And that is the expression that was given at the start of this section. So now we have this formula, and we could do a very similar proof by multiplying by a sine instead of a cosine, and we would find the b's. And let's jump back here to the